Additive manufacturing for the sustainable product development. This is the third technical webinar being organized by the II Kalburgi Local Center, and we are happy to continue our efforts to provide valuable technical knowledge and learning opportunities to our members and engineering fraternity. I warmly welcome our esteemed panelist, Dr. Shashank Patil, our moderator, Dr. Sharan Shegedar, and all the participants joining us today. I also sincerely thank the technical committee of II Head Office for their valuable support and cooperation in organizing this webinar. Thank you.
Thank you, sir. Respected Engineer Chandrasekhar Kakeri, sir, Chairman, IEI, Kalburgi Local Center. Respected Uday Shankar Ballari, sir, Secretary, IEI, Kalburgi Local Center. And hello. And all the officer bearers of the Indian Institute of Engineers, Kalburgi Local Center. Distinguished faculty members, researchers, professionals, and dear participants. It gives me immense pleasure to welcome you all to this technical webinar on Waste to Wealth, Additive Manufacturing for Sustainable Product Development, organized by the Indian Institute of Engineers, India, Kalburgi Local Center, under the aegis of Mechanical Engineering Division. I am Dr. Sharan Shegedar, and it is my privilege to be the moderator for today's technical session. The theme of today's webinar is highly relevant to the present scenario. Waste to Wealth focuses on converting waste material into useful and value-added products. Additive manufacturing, particularly 3D printing, provides excellent opportunity for sustainable product development through efficient material utilization, recycling, and the use of bio-based and waste-derived materials. It is now my privilege to introduce our distinguished panelist, Dr. Shashwat Patil, Assistant Professor, Department of Mechanical Engineering, Dayanand Sagar University, Bangalore. Dr. Shashwat Patil completed his BE in Mechanical Engineering from PDA College of Engineering, Kalburgi, in the year 2019, followed by his ME in Manufacturing Technology from NITTR, Chandigarh, in 2022. He completed his PhD in Mechanical Engineering from SIMATS Engineering, Chennai. Dr. Patil has an impressive research profile with around 13 Scopus indexed journals and one conference paper. His research publications cover important areas such as 3D printing polymers, composites, sustainable materials, bio-waste utilization, process optimization, and additive manufacturing. Dr. Patil has also valuable contribution in the area of innovation through 5 published Indian patent applications. Some of the notable patent includes sustainable material and processes in 3D printing towards eco-friendly manufacturing, sustainable fabrication technique for biofiller polymer composites, a focus on renewable resources, and he has also contributed to patents on high performance biofilter composites and biofabrication using 3D printing for organ regeneration. These innovations clearly reflect his interest in sustainable materials, eco-friendly manufacturing, additive manufacturing, and converting waste or renewable resources into value-added products. With his strong academic background, research, publications, and patent in additive manufacturing and sustainable materials, Dr. Patil is indeed a very appropriate person for today's webinar. On behalf of the Indian Institute of Engineers India, Kalburgi Local Center, I extend a very warm welcome to Dr. Shashwat Patil sir and thank him for accepting our invitation to share his knowledge and expertise with us. Sir, we are delighted to have you with us and we look forward to an insightful and enriching session. With this brief introduction, I now request Dr. Shashwat Patil sir to take over the session and enlighten us on waste to wealth, additive manufacturing for sustainable product development. Over to you, Shashwat sir. Thank you.
Thank you very much, sir. A very good evening to everyone. Respected Chandrasekhar Kacheri, sir, Chairman of IIA Kalburgi Local Center. Respected Seventh Secretary, sir, Professor, Department of Mechanical Engineering, Chandra University, who is also moderator of today's session. Distinguished members of the Indian Institution of Engineers, respected faculty members, researchers, students, and all the participants joining us today. It's my pleasure to be the part of this IEI technical webinar on waste to wealth additive manufacturing for sustainable product development. I sincerely thank Institution of Engineering Kalburgi Local Center and the Mechanical Engineering Division, and I would like to specially mention Vishal Dattoi sir for giving me this opportunity. Today, rather than looking at waste simply as something that needs to be disposed of, I would like us to look at waste from this different perspective, okay, as a potential engineering resources. Yes. If you look at it, why this sustainable product development it is getting importance nowadays. Okay. Growing environmental concerns demand eco-friendly materials and manufacturing processes. Circular economy promotes the conversion of waste into value-added products, reducing the environmental impact. In this, additive manufacturing enables this sustainable products to material efficiency, reduce the waste and design flexibility. Sustainable product development integrates renewable materials with the advanced manufacturing to create environmental responsible products. As you can see in this circular economy concept figure, as you see, this raw material has been manufactured and it has been distributed to the customer, and the customer using of this product, and it will be disposed, and disposed the product will be recycled again and used as raw material for the new product. And coming to the next, this cell waste. Why this cell waste is considered as a sustainable resources? Because you can see millions of tons of cell waste are generated annually by seafood and food processing industries. These wastes are rich in calcium carbonate, calcium phosphate, and chitin, making them valuable for engineering and the biomedical applications. This improper disposal of this cell waste causes environmental pollution, unpleasant odor like bad smell, landfill accumulation. Converting cell waste into Converting this cell waste into 3D printing biomaterial supports the circular economy and sustainable product development. Okay. Why this cell waste has been used in the biomedical applications? Because this cell waste material is having excellent biocompatibility, bioactivity, making cell-derived materials suitable for bone and dental applications. Okay. These materials are, as I already said, that these are been rich in the calcium carbonate, calcium phosphate, and hydroxide precursor, which is mimicry material of the bone material, which promotes this bone regeneration thing. Naturally available because it is natural available material, which is a low cost, it's a renewable, eco-friendly, supporting the sustainable healthcare solutions, suitable for like bone scaffolds, we'll be using dental implants, tissue engineering, drug delivery system. As you can see from this image, and it's 3D printing sustainable materials where they have been implemented on. Like as you can see, bone scaffolds provided a 3D structure that supports cell attachment and bone regeneration. As you can see in the dental implants also, many nowadays advanced technologies has been improved in the additive manufacturing process, which enhances the also integration and improves the implant stability. then in the tissue engineering as well as in the drug delivery system. Then why this additive manufacturing role plays an important in the biomedical engineering field. Okay. Uh, Using this additive manufacturing technique, we can implant or we can print or fabricate the patient specific implant can be fabricated with high precision using medical imaging data. Okay. The complex porous structures improve this osseointegration and promote the bone tissue growth. As this today topic is covers this interdisciplinary part, as it will be covering the mechanical part as well as the biomedical part, okay, biomedical applications. Minimal material in this additive manufacturing plays important role here as compared to the subtractive manufacturing process where material is being with subtractive manufacturing. In this additive manufacturing, we'll be loading the material wherever it is required. So minimal material waste will be there in this one, and it is having the rapid prototyping making additive manufacturing a suitable manufacturing process. This bio-based composite material, including this cell-derived for use for my study, which can be processed into customized biomedical products. Coming to the technique of fusion diffusion modeling, which is a part of additive manufacturing technique. Okay, it is a computer controlled process that builds a 3D dimensional object by adding a material one layer at a time, usually directed from a CAD design. As it is saying that it will be building a layer by layer fabricated as mentioned from the CAD design. Okay. Usually in the subtractive manufacturing material, imagine if you have taken one square rectangle, in that if you want to make any design or anything, we will be making a hole and removing the material. So in this additive manufacturing technique, what we will be doing, we will be adding the material wherever it is required. So material wastage can be avoided using this technique. Okay. Then fusion diffusion modeling is mostly widely used polymer-based 3D printing technology. Why? Because due to its simplicity and cost effectiveness, and it is a user-friendly technique. Okay. Anyone can, those who don't have basic knowledge also, if they learn within a few minutes, they will get to know about this technique. Okay. This it has been compatible with the biodegradable polymers such as the PLA and biocomposite filament. This enables rapid fabrication of customized biomedical prototypes with minimal material waste. As you can see, this is the FDM process where, as you can see, this filament spool, where the spool is loaded and it will be loaded into the drivers. And here in the extrusion head, you can see liquefier is there, where it will be getting heated zone will be there. And after heating through the extrusion nozzle, the heated material will be loaded and it will be built on the platform according to the mentioned design by the CAD design. Okay. Then coming to the next slide that shows us my main material what I have taken for my study. That is the matrix material. I have taken polylactic acid. Why this polylactic acid I have taken? Okay. PLA is a biodegradable, biocompatible thermoplastic, making it suitable for biomedical and sustainable applications. It offers excellent printability using the fusion diffusion modeling, enabling the fabrication of customized structures with use. However, this PLA, okay, has having some limitations also, including this mechanical low strength and poor thermal resistance. Reinforcement with natural fillers can enhance its performance. So what I have done is to improve this mechanical strength and its thermal resistance, we have reinforced it with natural fillers material to enhance its performance. Okay. As you can see, the process of this PLA production, it is like starch material from the starch. They have been plant-based source. They have extracted and they have done the bacteria fermentation. Then they have done the polymerization. Then the product is available. Okay. Then coming to the next reinforcement material. Why I have used this quick pen powder for my study. This is the marine bio-waste rich in chitin and bioactive mineral, making it promising reinforcement material. Usually this sweet fish pen powder, they are using for this birds food they have been using. I got to know that when I was doing research about this one, why they are using for this. After that, when they were eating this one, the cell they are using for this part for making food for that cell powder they were taking and they were using for pet powders for the birds and all. Okay. This powder contains constants similar to our natural bone, including the calcium phosphate, phosphorus, titin, which supports the bone tissue regeneration, which enhances the mechanical strength and the bioactivity of the PLA composites for the our dedicated biomedical application, which can, it's also helpful in the circular economy by converting this seafood waste into high value biomaterial, supporting the circular economy and sustainable product development. Okay. I have gone through some refresher survey from the previous what they have done, previous people, what the research they have completed. Then I got to know that this marine derived fillers like fish bone powder, calcium carbonate, this hydroxypate, they have improved the mechanical properties of the PLA through up to like 15% of the reinforcement material if you are using in the mattress material, which enhances this mechanical property strength and its biodegradability. While if you are using more than that percentage, its performance will be reduced. Then this quick fan powder will not be studied, were studied for the biomedical purpose, but using this 3D printing technique, no one has studied this working. Then in this what research I have followed it, that this present study develops the characterization of 3D printed composites reinforced with, I have done with a three type sets of experiment. One I have done with treated solution, chemical solution treated materials powder, one with the untreated powder. And then I applied some optimization techniques to enhance the applicability certainly. So if you are looking at my studies, like even what I have studied, like if I want to say it, I have developed and optimized the 3D printed polylactic acid composite reinforced with untreated and the saline treated strip and powder, and to evaluate their mechanical, thermal, morphological, antibacterial properties for potential use in this application. Okay. Coming to the main part of the session, like what methodology I use and how I fabricated this material. Okay. First, I have collected the raw material. Then for the raw material, reinforcement material, I have done the chemical treatment. And then for the after the chemical treatment, I have used mattress material and the filler material. I have done the filament extrusion. Then I have tested the filament for the application purpose. Then I have fabricated printing using 3D printing. What all the tests I have conducted, I have shown in the just overview. Here I have conducted this mechanical test in that included of tensile, flexural, compression, and impact. And in coming to the thermal test also I have done. Then I have done thermogravity analysis and DSC. And I have done antibacterial properties. Since we are using for this biomedical, so that to test that, I have done also antibacterial test with a minimal inhibition concentration. Then I have done structural properties and the morphological, which using STEM, INEX, XRD. And coming to the statistical analysis using this response surface methodology. Okay. As you can see, the material which I have used for the study, you can see. I have used the polylactic acid granules and I have taken this extracted this fish pen powder and this third C image shows this mixture of this both particles. These are the material properties of my biomaterial properties, and they're for the polylactic we are like it is having the density of 1.64 and the melting temperature of up to 150 to 160. It is a biodegradable and compositable. When it comes to the split pen powder, it is having the density of 3.6 to 2.9. And for our study, for particularly for using for this 3D printing filament purpose, the reinforcement material should be less than 50 microns. So that we have done ball milling process and all. Then, as you can see, like how I have extracted this squid pen powder I have extracted. I have collected this squid pen fish powder from Kanyakumari region, C region, coastal region. Then I have collected which is having the size length of 9 to 12 centimeter range of length and 5 to 8 centimeter of the weight and 0.2 thickness. Then firstly I have done pre-treatment of this fish powder because to remove the dirt from applied on it, remove the dirt and everything, impurity. Then I have dried using the oven. Then after drying, I remove the outer layer shell and I use the pistol and grinder for the crushing of the material. For the further grind or further improvement of material, which is making it below like 15 micron, I'll use the ball milling technique. Then I see the machine and attain this split pen flavor. Coming to the next, like I said that I have done two sets of experiment, two sets. One with the untreated without treating anything and mixing with the PLA. One I have done with the chemical treatment. What this chemical treatment will help us that to study that purpose I have done this. First I have surface activated with the acetone. With acetone I have surface activated this pigment powder. Then with after filtering it out, then I use the saline solution with trimethyl imine solution and ethanol and distilled water. I have kept it for like with a pH estimation, but for 24 hours I submerged this powder in this chemical solution. Then I have filtered out that process and I have dried in the furnace for like 6 to 8 hours. Then this chemical treated hydroxide material I have been extracted. If you look at, okay, what major difference I have attained from this untreated and treated material, as you can see. For AB images shows for the untreated saline samples and the C and C show for the saline treated samples. As you can see in A, there is a high porosity from the sun image we got in that there is a high porosity and there is an interfacial gap between and there is accumulator. The particle gets accumulated. Okay, but when we have done this saline treatment, the porosity has been reduced and this it is interfacial has been improved and the hydroxide has been better dispersion. There were no accumulation particle present in that. Then we have tested for that proof. We have done this chemical properties with the EDAC material. This, as you can see, image A shows this EDAX analysis of untreated sample and B shows for saline treated. As you can see in the A material, it is having the more percentage of carbon content, carbon weightage percent it is having due to dirt material and all. Since we have used the saline treatment, this carbon content has been reduced to 6.79%. And as you can see from the calcium also, it was 40.81 in the untreated sample. Whereas after the saline treatment, it has got improved to 56.95. And the major proof of our study that saline treatment has got bonded with strip model. It has been proved through this EDAX analysis by, as you can see, the silicon particle has been attained from 2.45%. Then we have done this structural analysis. Okay. In the structural analysis, as you can see, it shows this crystallinity percentage and amorphous percentage of untreated and the treated samples. They were the major peaks around from 20 degree to 50 degree as it was calcium carbide in the form of calcite. But after treatment, the crystalline form has been reduced slightly and the amorphous content increased from 19.7% to the 20.6 percentage. It shows that without disrupting this original crystalline structure, the material has been bonded to the like saline protein has been bonded to the split fish sun powder. Okay. Coming to the like compositions, like how we have splitted up and composition we have done for our study. We have done two sets, as I said earlier. In that two sets, in single one set, we have done three compositions of 97% of the matrix material of the PLA and the 3% of the filler split pen powder and 3% and the 6% and 9%. Similarly, we have varied for 3, 6, 9 for the saline treatment. Then comes the next how we have fabricated this composite material, how we have fabricated this composite filament. Okay, as you can see, we have taken this granules of the PLA and the split pen powder we have taken. Then we have mixed it, and after mixing it, we have fed it into this filament extruder. Using this filament extruder, we have fed our material into this filament extruder. and at the temperature around 180 degrees, we have heated in the heated zone, and it's the process of in the nozzle. This nozzle contains of 1.75 diameter. It is a standard diameter size for printing material for already equipped market size of nozzle is 1.75. That we have extracted this good composite material. Then immediately for we have done the water bath, and using this diapers calorimeter, we have measured that whether this fabricated filament is having this 1.75 diameter, and then we, with a spoon help, we have welded it. And with this heated and untreated sample, we are using this 3D printing, Creality open source 3D printing. We have printed the sample according to the ASTM standard. Then what are the printed parameters? As you can see, we have used for our study of the composite filaments. We have used a layer thickness of 0.1 mm for our study, and nozzle temperature of 220 degrees, and infill density of 100%. We have given the infill density to strengthen the material, and the print speed of 40 mm, and nozzle diameter of 0.4 mm for the print, and the bed side we have kept at 60 degrees. As we can see, the printed samples of the tensile sample according to the ASTM D638. After the printing of the sample, we are using for tensile test using this UTM. As you can see from this image, we have placed our sample in a vertical position and clamped the UTM machine. And this is the flexible sample according to the ASTM standard D790. And this is the compressive test sample. According to the ASTM standard D695, we have printed the sample and placed in the UTM machine. And this is the impact sample, ASTM D256 sample, and the impact of wheel strength, nozzle strength, we have 6 samples we have printed. And this is the experiment setup for thermogravity analysis. We have spread up after each composition of untreated samples and the treated samples. And then this is the antibacterial activity setup I am showing it. First, using this agar powder solution, we have dissolved it in distilled water. We have poured our solution and we have dissolved for 1 hour, 2 hours. Then we have sterilized to remove the bacterial pathogens and all. We have sterilized using autoclave setup. Then the prepared autoclave solution, we have poured in the Petri dish plate, and we have inserted our solution and tested with the 2 types of different bacteria, that is E. coli and Staphylococcus aureus. Well, coming to the result parts of the study, what I have done, if you can see from the result, this influence of this quick fine powder biofillers on the tensile properties of the PLA composites. As you can see, the 2 sets from the untreated part, 6% of the filler is giving the maximum strength of 26.20, whereas for saline treated, it has shown that improvement of 28.88. As you can see, for this 3% filler, we have attained the minimum of 19.3, whereas for the saline treated, 21.66. It shows that saline percent, the 6% filler, if you are using, it is giving this maximum strength. As you can see from this stress strain diagram, the saline treated sample of 6% filler composite shows the highest tensile strength. The treated sample recorded at highest tensile along with the treated 7%, indicating superior ductility attributed to the improved matrix addition following this surface modification. Yes. As you can see from this bar graph, the saline treated 6% showed the highest tensile strength of 28.8, showing an overall increment of 8.4% percentage compared to this untreated composite due to this improved this interfacial bonding and matrix thickness. Then coming to the flexible sample test result, here also like for the 6% of filler, we have attained the maximum strength of 58.3, whereas for untreated we have attained 51.40. If you can see overall, 6% of the saline treated samples is giving more strength compared to the untreated sample. This is a sustain diagram for the flexural strength. As you can see from this, the treated PLA composites with a 6% shows this maximum, okay, maximum flexural strength. The composites show the highest structural strain of 5.3%. This is showing this greater deformation capability compared to the other previous samples. This is the bar graph of change. This is showing that 6% of filler. It is showing overall increment of 12.5% when it got compared with the untreated samples. And then these are some of the results of compression. Here also, as you can see, 6%. Why this 6% is giving more sense if you got to know me. With the 3% of it will be a minimal filler percentage. So maximum matrix material will be contained of PLA only, so that it will be showing a limited strength. As for excessive 9% filler, it is also reducing strength as compared to the 6%. As studies from the literature studies, if you are accessing the filler material, the strength gets reduced. So this treated 6% composite exhibited the highest compressive strength, significantly over untreated sample. As why all the time this treated sample is showing the more strength compared to the untreated, means this filler matrix interaction and uniform distribution has been attained for this sealant treated particles. And this is the impact ISO test sample results. Here also we have attained 10%, 10.2 strength for 3% of untreated, whereas for 6% we have attained 14.4, and the maximum we have attained 20.2 for the 6% of treated sample. These are the bar graph results. So, coming to the thermal properties, okay, the influence of this reinforcement material influence of the PLA, as you can see, usually the PLA material gets usually melting rate like 150 to 160 range of melting temperature. So with the composite material, the onset temperature it got started at 265, where the material gets started heated degrading, and it reached till 283 degree. Whereas for maximum of 6% sealant filler, we have achieved maximum of 337 with the final residue, that is ashes of powder after burning. We have achieved maximum strength, maximum withstand for this 6%, that is of 11.5%. This is the image showing the refrigerator. As you can see from this, with the temperature of starting from 50, we have given started from 0 and till this 325 degrees, then the heating zone starts. Then its material gets degraded, and after that around 337, it got the final restoration. This is the differential scanning calorimeter. As you can see, TG is a glass temperature, TC is the crystalline temperature, and TEM is the melting temperature of the sample. We have achieved the maximum of 60.2 for the 3% of the sealant treatment, and crystalline temperature of 110 degrees, and maximum of melting temperature at 149. These are the results in its shows. As you can see, this first peak is showing that first peak shows that glass transition temperature, and second lower peak shows that this is lower degrade stage, crystalline stage, where the cooling stage will be happening. Then again in the melting stage, it shows that peak of 149.6. Then coming to the next, shows the antibacterial test results of the sample. As you can see, with the concentration increasing, the material that zone of inhibition that increase. As you can see from this result, for the 0.1 percentage, 0.1 concentration, we have achieved 1.3 to 1.5. For E. coli, we have achieved 1.3. As far as Staphylococcus aureus, we have achieved 1.5. As we are increasing the concentration, we are being seeing this zone of inhibition is getting increased. For the total full of 100% concentration, we have achieved the maximum of 9.3, and for zone of inhibition for Staphylococcus aureus, we have achieved maximum of 11. As you can see from this graph, the antibacterial effect increased with a higher concentration for both E. coli and Staphylococcus aureus bacteria, demonstrating this a clear dose-dependent response. This Staphylococcus aureus shows slightly higher sensitivity across all the concentrations compared to this E. coli, suggesting its greater susceptibility to the tested agent. Coming to this microstructure analysis of the printed fabricated sample, as you can see from this untreated fabricated sample of the test filament samples, you can see there are many voids and there is some fiber pull out from the sample, and there are many micro cracks have been shown in this untreated sample. Whereas compared to the untreated, you can see from this treated sample, which like include interfacial addition, there are cracks have been avoided and fiber fill out has been reduced. This shows that our saline treated sample improved this study. Then coming to the statistical analysis. Why we have done this statistical analysis means to get clear idea about without doing more experiments, with getting that what combination will be giving us for like more strength. To do that one, we have done the statistical analysis. We have defined this output response to be optimized. Then we have identified the design factors and their levels that we have done 3x3 levels for our study. Then we have developed this response surface model in. Then using the CCD design, we have obtained this we have obtained the output response. Then we have done validation. We have done multi optimization study. Then we have defined the optimum set of values corresponding to the output response. As you can see from this experimental design, yeah, I already said that I have taken three input parameters and the three output parameters. I have taken the three input parameters range of layer thickness from 0.1 to 0.3 range, whereas the nozzle temperature I have taken range from 180 to 220 degrees, whereas for the film I have taken from like 3 to 9 degree variation. For that different combination of sets, I have done the experiment. I have attained these results. I have mentioned for the tensile strength, flexural strength, and the compression strength. Total of 19 experiments have been performed for this study with the different combinations. As you can see from this, 0.1 ratio 190 degrees and 9% is filler. 0.12 not 5 degrees, 6% is a filler. Like this variants we have been performed. Then, if you can see from this obtained graph, it is predicted value which is suggested by the software, RSM software, and the actual value we have attained from our experimental results. As you can see from these three results or three responses, for the reference line, the values are near to the reference line. It shows that our predicted value is suggesting that our experiment values are near to the predicted value. And these are the some surface plots obtained for our study. As you can see, this tensile strength with respect to nozzle temperature and layer thickness, tensile strength properties, and filler ratio and layer thickness for the tensile, and for filler ratio and nozzle temperature, keeping the third parameter as a constant. As you can see, as the layer thickness, if you are increasing, the nozzle temperature at the moderate temperature of 310 degrees, we will achieve the maximum flexural, tensile strength. That you can see from the next image, that the image figure B, as you are increasing this layer thickness and filler ratio increasing, the strength reduces. So at the moderate of 6% of filler and layer thickness of, if you are keeping at 0.2, we are getting the maximum tensile strength. Then coming to the next lecture, as it says, two parameters are being varied and one parameter kept constant for the flexural. As here also, as the layer thickness and nozzle temperature, if you are keeping the nozzle temperature at 310 degrees and the layer thickness of 0.2 mm, we have achieved the maximum flexural. Similarly, for the composition, with the increase of layer thickness and the increase of nozzle temperature, the strength get reduced. As you can see from this image, the reddish color zone shows that it is strength getting reduced. Okay. Then next, this coming to this multi-objective optimization, as this data says that for our study, we have used three input parameters and the three output parameters. In that minimum level of the output parameter and the maximum level. For the minimum level, how much strength we have achieved as being shown in the right side of the response output. For the maximum, what we have achieved that has been shown. And we have kept in rates for the input parameters, whereas for the response, we have kept the maximum strength. Yeah, because we need to attain the maximum strength for our material so that then the optimized results show that in the software, it is suggested that if you are keeping this layer thickness of 0.3, nozzle temperature of 250, and the flexural ratio of 6%, we will be achieving the maximum of 36 for tensile strength and the flexural strength of 56.8 and the compression strength of 38. And this is showing the desirability of 0.9. It is showing that error percentage is less than 5%. So to confirm this optimization result, we have done the validation test. We have done triple K test for the validation. We have attained like for the predicted and values, it was suggested that 36.43 for the sample. Through our experiment, we have attained, through the average value, we have attained 35.09, whereas for the flexural, we have attained 55.15, and the compression, we have attained 37.15. This, in this all three, we are near to the predicted value, and the error percentage is less than 5%. This is acceptable range, and this shows that our model is suggested significant. Then coming to the last part, conclusion, like I'll be concluding in the general way rather than going in the technical way for concluding. Like why waste we should be always used as end material life. It can be begun of another product life also. Since this additive manufacturing gives us opportunity to transform this concept into reality by enabling this conversion of waste derived material into this functional and value added products. However, achieving this true sustainability requires more than simply using the base in 3D printer. We need to consider this entire material lifestyle from waste collection and process to feedstock filament development and this printing and the product performance using recycling to end to life. This real opportunity therefore lies at the intersection of waste valorization, advanced material, additive manufacturing, and sustainable product vision. These are some reference I use for my studies. And this is my scope of profile page. I published around 18 publications, around 9 exhibits and 450 plus citations. Sir, current,
Hello, Shashwat sir. Okay.
sir,
Shashwat sir, thank you very much for that excellent and insightful presentation. You have given us a very clear understanding of how additive manufacturing can contribute to sustainable product development and convert waste material into useful and value-added products, sir. The example and research insight, whatever you have shared, particularly related with the 3D printing and sustainable materials, as well as bio-waste composites, uh, were highly relevant to today's theme, sir. I'm sure this session has given all of us several new ideas and perspective for our teaching, research, innovation, and future projects, sir. Once again, sir, on behalf of the Institute of Engineers India, Kalburgi Local Center, I sincerely thank you for sharing your valuable knowledge and expertise with us, sir. Now it's a time to question and answer session, sir. I request all participants to actively participate and make the best use of this opportunity to interact with our today's speaker, Dr. Shashwat Patil sir. If you have any questions related to additive manufacturing, sustainable materials, waste utilization, kindly ask the question. Feel free to ask your question. I request participants, if you have any questions, please. Hello. Okay. Shashwat sir, there are a couple of questions which has been asked in the chat box. Just go through and kindly answer them, sir.
Sagar Kulkarni has asked that please provide some business initiatives for biodegradables in additive manufacturing in Bharat. Since for the biodegradable, there are many polylactic acid, like PETG, many like materials are available as a biodegradable. So you can start in the business idea of like extruding them, filament, making it a filament using filament extruder and making it to the 3D printing product. It's under Bharat Innovation. It's like around small scale business we can be able to do in. Then another question asked by Ranjit Singh. A significant amount of material waste is generated in automobile, forging, machining, fabrication, and other manufacturing industry in the form of machining chips, metal cut chips, leftover plates, forging flash and rejected components, and other processes. How can we control and minimize this waste at manufacturing stage? How can we remain waste be converted into value instead of simply being sold as scrap? Okay, as I informed early, this what you are saying, Ranjit sir, it's comes under this conventional manufacturing process. So since to make a product, we will be doing this machining process and we will be doing this wastage material. So to overcome this and all, this additive manufacturing techniques came in that wherever that I already said that instead of removing the material, here we will be adding the material wherever it is required. Okay. Since imagine you can take on cube, okay, take on cube rectangle part. In that I wanted to make an hole. Okay. In the conventional machining, what we'll be doing, we'll be making it whole and we'll be removing the material and we'll be showing the HS for the end product. Whereas in the 3D printing, while designing itself, I'll be making it whole line and I will be making it hollow and I just giving the command that it should not be get printed. So since by doing this additive manufacturing technique, we can be reduced the waste. And as you asked in the trap instead of converting into trap, this will be very useful for us.
Dear participants, do you have any questions? Feel free to ask.
Okay, as Pankaj asked, what is the maximum dimension of the product we can achieve by 3D printing? Since for the existing market technology by the 3D printing, it ranges from 150 dimensions to 600. Recently, in our college, only in the Dayanand Sagar University, they have got a Preetham made company, that is Indian company, which is having the batch size of 600 into 600 into 600. As I think I answered for Pankaj Jadhav. Then
Yes, sir.
for
Thank you.
VS,
Thank you, sir.
yes, sir.
Another couple of questions posed by Viresh Bodhi sir and Narendra Kumar Sharma.
Yes, sir.
So Viresh Bodhi sir uh, has asked, how can we balance recyclability, mechanical performance, and repeat reprocessing of polymers in a circular additive manufacturing system?
Yes, sir. That,
Kindly help.
yes, sir. That I suggested, like, how can we balance recyclability? Since the material, like, we can go for primary, secondary, tertiary, we can be going. Beyond the secondary and tertiary, the material strength will be reduced. And for mechanical performance, you are saying, using the reinforcement material, we can improve the strength and repetitive those resistance in this polymer part. For the Narendra Kumar, can you tell something about waste plastic material processing into raw materials for plastic bottle industry? Yes, that I have suggested now. As we can be taking this PETG, polymer, PLA, polylactic acid, different types of plastic material. We can be taking this material and we have to using this extrusion. We can be making it into the filament form, and using this filament form, we can be able to print in the bottle industry as the bottle industry or the market related market. Even in this as you all know, for the pipe also for domestic purpose, what we will be using, this is also printed in the same ways of using the different plastic material.
So,
Thank you, sir. I think I have
okay, sir.
answered all the questions, I guess, sir.
Uh, Thank you, sir, for patiently answering the questions asked by various participants. So now I request Mr. Prashant Mulge, sir, Assistant Professor, Shanbasova University, who is a honorable member of Mechanical Division of Kalburgi Local Center, to propose vote of thanks. I will hand over this to Prashant Mulge, sir.
Good evening, everyone. It's my privilege to process the vote of thanks on the occasion of today's online webinar organized by the Mechanical Engineering Division, Local Center, the Institute of Engineers, India, Kalburgi. First and foremost, I express my sincere gratitude to our esteemed resource person, Dr. Shashwat Patil, for delivering an insightful and informative talk on waste to wealth additive manufacturing for sustainable product development. The session provided valuable insights into how additive manufacturing can transfer waste material into useful and sustainable products, contributing to innovation, resource efficiency, and sustainable development. We sincerely appreciate Dr. Shashwat Patil for sharing his valuable knowledge, expertise, and practical perspectives with us. I take this opportunity to express my heartfelt thanks to Engineer Kakeri Chandrasekhar sir, Honorable Chairman, IIA Local Center, Kalburgi, for his continuous support, encouragement, and guidance in organizing such meaningful technical activities. I extend my sincere thanks to Engineer Uday Shankar Bellari sir, who is a Secretary, IIA Local Center, Kalburgi, for his valuable support and coordination in making this webinar successful. I also express my gratitude to Dr. Vishal Dutt Koir sir, Executive Member, IIA Local Center, Kalburgi, for his presence, support, and encouragement. My sincere thanks goes to Dr. Sharan Shigedar, moderator of today's webinar and honorable member of the Mechanical Engineering Division, IIA Local Center, Kalburgi, for efficiently moderating the session and ensuring its smooth conduct. I would also like to extend my heartfelt thanks to all the participants who took their valuable time to attend this webinar and actively participate in the session. Your presence and interest have truly contributed to the success of this program. Finally, I thank everyone who has directly or indirectly contributed to the successful organization of this webinar. Once again, I extend my sincere gratitude to our resource person, dignitaries, moderator, organizers, and all the participants. Thank you, one and all.
Okay, thank
Karan sir. Hello, Karan sir.